In today's episode, Frederic Detienne takes us back to the early days of cryptography.
In the beginning, we had algorithms that we thought, they're good enough, like DES,
They're very
MD5.
good, actually. They were not just good enough, they were excellent for the time.
Discusses AES, elliptic curve, and Diffie-Hellman.
You can expect that maybe in 5 years or something, we'll be discussing or be at the replacement of AES. It's quite likely.
And takes us through post-quantum cryptography. So buckle up.
Welcome to Cisco Tech Stories, a podcast with real-life stories from real-life engineers. Your hosts are Nicholas and Tristan.
Welcome back to Cisco Tech Stories, the podcast where we interview Cisco subject matter experts and hear their craziest troubleshooting story, their take on the latest technology developments, or where we deep dive into the technology shaping our world and the innovators behind it. I'm Nico.
And I'm Tristan. We are excited to bring you a special double episode today, where we will be exploring the fascinating intersection of cryptography and quantum computing. Two topics that are not only shaping the future of security, but also the technology landscape as a whole.
In our first segment today, we're joined by Fred Detienne, Distinguished Engineer at Cisco CX. Frederic has spent years at the forefront of cryptography, and today he'll walk us through the evolution of crypto from its early days right up to the challenges quantum computing brings, and how post-quantum cryptography is already there and stepping up to meet them.
Of course, you can't talk about post-quantum cryptography without talking about quantum computing itself. And for part 2, which will be airing next month, we have invited Tim Tsigari, who help us unravel the mystery of quantum computing, what it is, why it matters, and what it means for the future of security and technology.
Whether you're a crypto enthusiast, a quantum skeptic, or just curious about the tech shaping tomorrow, you're in the right place. So let's jump right in.
Starting with our interview of Fred Detienne.
Hey, Fred.
Hello, guys. How are you?
Good. Can you introduce yourself? We had you already on the show, but can you reintroduce yourself with this context?
Yeah. My name is Frederic Detienne, Frederic Detienne in French. I'm a French speaker. I usually go by Fred for whatever reason. It upsets my mom, I guess. I'm Distinguished Engineer. I've been with Cisco for 28 years, I think, something like that. And for a long time, I have been architect and inventor for crypto products, so DMVPN, FlexVPN. So this is how I started my journey in cryptography. And to date, it sticks with me as a hobby, as a pleasure. I still like to follow the evolution of cryptography. And I have a couple of presentations at Cisco Live that deal with security, and one of them is cryptography based. So
that will be today's game, because I had a few questions about crypto, the latest developments, the latest news. Like I learned about crypto at school, but it didn't cover these latest features and trends. And I did ask some questions to various AI and got some answers. But let's see if you can do better than the AI. If humans still beats the AI in explanation.
let's see that.
So maybe let's start with the basics if we can, right? So cryptography started with various codes. I'm thinking about the Caesar's code, which is just like, let's just scramble the data. But it's not necessarily harder to decrypt it than to encrypt it. So that's the problem when you do use a random method. It's not very efficient for computers. And then since the early days of computers, we had to find methods where encrypting is easy, but then decrypting is hard when you don't know the key, right? And that's the whole premises of the MOT-P system. Is this correct, or am I completely off?
Yeah, so the Caesar cipher, which is usually called ROT13 if you just shift the alphabet by 13 letters. So Caesar cipher is simply like a letter swapping or letter shifting algorithm. It suffers from many, many problems. So for one, the key size is very short. You can only shift the alphabet by 26 letters. Right, you can move A to Z or to Z. If you move it one more position, A becomes A again. All right, so the key size is literally 26. It's very, very short. You can try all the keys like in a snap. Because the block size is also short, it's one letter, right? So you can replace one letter with another letter. The block size itself is also very short, and it means that you can conduct a statistical attack on it meaning that if you count the number of occurrences of the letter A, B, C, D, etc. in the cipher text, so the encrypted text, the letter with the highest frequency, let's say it turns out to be X, will actually be the mapping of the letter E in English, statistically speaking. So if you know you're dealing with an English text, you look for the encrypted letter with the highest frequency, and you're pretty sure it's going to be an E. If it's not an E, it's probably going to be an A. And once you know that X is A, you compute the difference, and you know the shift, and you have the key. All right, so these are a couple of problems that you have with the Caesar cipher. There's plenty of other problems. And so modern cryptographic algorithms, they have a long block size, so they encrypt multiple bytes or multiple letters, if you wish, at the same time. So usually it's 128 bits, something along those lines, 256 bits maybe sometimes. The key size is also a lot longer. So in this case, the number of possibilities is not 26, it's 2 to the power of 256, all right? So it's like massive, all right? So more than there are atoms in the universe, just to give an idea.
More than IPv6 addresses.
Yes, yes. With 128, you're at the same size. Everybody has the internet for himself or hers for themselves, but yeah, with 2 to the power of 256, it's a massive key size. So that's the kind of strength that you want to have, that an attacker, when they do an exhaustive attack, it shouldn't cost them less than 2 to the power of 128, and ideally as close as possible to 2 to the power of 256, because it gives you some leeway in the phase of the evolution of mathematics and computing power. And that would be typically the strength of AES 128 or 256. They're a little bit weaker because there are some mathematical attacks on that. But yeah, that's about the strength of AES, of symmetric algo.
If I can ask a question here. So the reason why cryptography today is secure is just because it statistically take an enormous amount of time for computer to break the numbers that are used for encryption. Therefore, if you get that number, if you manage to get that number one way or the other, you manage to break the encryption.
Exactly. It's actually an easy computation for the legitimate participants. Let's say you encrypt a piece of text and you send it to Nico. It's reasonably easy for you to encrypt. It's reasonably easy for Nico to decrypt. It still requires a little bit of computing power, but like a very old phone can do it, right? Like a simple step. But if an attacker tries, even if they know the algorithm, if they know exactly how the message was encoded and all they miss is the key, then they are unable to decrypt in a reasonable amount of time, reasonable being, depending on the sensitivity of the data, a few years to about 30 years for super secret information. 30 to 40 years. That's how long we want to keep the data secret. And today we aim for systems that have as far as possible or as long as possible resistance to crypto or cipher attacks or attacks in general, but certainly plain text. And plain text today would cost you millions of years. But mathematical attacks, right? That's always the key element. And also the power of 2 in computing power, right? Every year you double. And the power of 2 is a pretty nasty attacker.
And that's why algorithms like DES and 3DES are nowadays crackable.
Yeah, what used to take thousands of years of computing power in the 1970s, 1980s, now takes roughly a couple of hours on reasonable hardware, like some couple of GPUs, and you're off to the races. Why? Because mathematically DES and triple DES have become a little weaker. There are shortcuts that simplify or reduce the search space, but at the same time, hardware has progressed, and in 30 years, you make progress 2 to the power of 30.
So is it correct to say that in the beginning, we had algorithms that we thought, they're good enough, like DES,
very
MD5.
Good, actually. They were not just good enough, they were excellent for the time.
But then they said, maybe, in the short future, maybe they will be breakable, but it's okay. We can just increase key size. I'm thinking about RC4 as well. Let's just put, a bigger key size, triple DES. Let's just run it 3 times in a row.
Yep.
But people found weaknesses that, like, okay, if you try all possibilities, it's not easy to break. But like you said, we have shortcuts. And if you look at frequency, if you look at this, the search space is reduced and then it becomes manageable. So now we move to algorithms that to this day have little to no shortcuts, like AES, SHA, etc., right?
They do have shortcuts.
Right.
So literally right after AES was made a standard, a couple of weaknesses have been discovered and the strength of the system has decreased. So we used to recommend or say that AES 128 was good enough, it's very likely that in the next couple of years, we will recommend AES 256 as the minimum. And you can expect that maybe in 5 years or something, we'll be discussing or be at the replacement of AES. It's quite likely. I don't have a crystal ball. You never know how far is going to happen. Surprise developments may accelerate things, but yeah, in about 5 years, I wouldn't be surprised if AES was, the talks, or it was in good progress of replacement.
They have weaknesses so far less than previous algorithms, right? Like they're still
Oh
holding
yeah,
good.
it's always better. Yeah.
We just increase key size, but then it's not reasonable to increase key size all the time. Right now, 1,000 bit, like it's not going to be practical.
Well,
So
actually,
you need to find a
you
better.
can't. You can't even do that. So AES has a hard-coded limit. If you wish to 256, you would have to redesign the algorithm to increase the key size. It was built to have 128 and 256 bits key size and also 192, but nobody ever used that. Hardly anybody uses it. But AES was built to have 128 and 256. The block size, same thing, it was 128. So AES over DES, for instance, was a huge optimization in computing time. It was very efficient to compute compared to DES, because DES didn't care about byte alignment, for instance, or using entire bytes. It went down to the bit level, and you had to do some really complicated operations. So DES was actually reasonably expensive to compute, to use for encryption, where AES was also optimized for the current CPUs, and it can only do 128, 192, and 256. It won't go any further. The algorithm that you're probably thinking about that can increase key size are stuff like public key algorithm, like RSA or elliptic curve. These have a modulus length, so that's ECDH, for instance, or elliptic curve digital signature, using a modulus of typically 256 bits, but you can expand that. Or RSA, that used to be 1024 bits long modulus and became 2048, and nowadays we recommend 4096 bits. That's the modulus length. You can think of it as the key size or the key strength, but you have to know that a public key algorithm has a much weaker strength than a symmetric algorithm. So public key algorithm are algorithms for which the encryption key and the decryption key are different. Symmetric, it's the same key that you use. And so where a symmetric algorithm usually has a key, has a strength that is close to the key strength, so the attacker has to brute force attacker, right, has to perform as many operations on a symmetric algorithm as the length of the key, roughly, bearing attacks, like mathematical attacks. In a public key crypto system, you have 1024, 4096 modulus length, but the key strength does not reach 256. Right? There are shortcuts by nature in these algorithms that mean that a brute force attacker has less combinations to try. It's less strong.
Just the fact that you have to produce two keys that work together, right?
Yeah, it's the whole mathematics behind, and the difficulty is that to increase the strength of these algorithms significantly, to go from, let's say, 128-bit security to 256-bit security. So it's really a misnomer. When we say 128-bit security, it means 2 to the power of 128 operations to do a brute force attack, right? So that's that's how we should say. It's just longer. And so to increase from 128 to 256 RSA, you have to bump the RSA key size to 8,000 bit or something like that. It means that you actually are dealing with numbers that have 8,000 digits long. You don't do this on the 64-bit architecture. I mean, of course, we do it on the 64-bit architecture, but you have to have implementations of computations like big nums that do not use the CPU operations for multiplication, addition, etc. You have to implement multiplication, exponentiation, and all of that in software. All right, you have to have piece of code to do these multiplication on these very, very large numbers. And they're exponentially more complex or more time-consuming. So where we said it's reasonably easy for the legitimate users to encrypt and decrypt, and it's complex for the attacker to do it, well, we're increasing the complexity way too much on the users. That, and also the weaknesses in math with the quantum computer looming on the horizon.
But you started with one word that I want to click on, elliptic curve. To the average network engineer like me, you had your crypto background, but then you didn't check what was the latest. Suddenly it seems like elliptic curve is the second coming of the Messiah. What does it change to the algorithm?
So there are two algorithms today used widely. I'm talking about public key encryption. So public key encryption is the algorithm that you use for key exchange, so ephemeral secret generation, and authentication. All right, so you start a TLS connection or an IPsec-I connection, or you authenticate on a wireless network. You do two things. So first, you negotiate ephemeral keys, which are keys that you're going to use with AES a little later. Why? Because AES is a lot faster at encrypting and decrypting, but you don't want to use the same key all the time. So you create an ephemeral key using Diffie-Hellman or elliptic curve Diffie-Hellman, and then you authenticate. So you prove that you're Nico, you prove that you're Tristan through the other party, and the other party proves that they are really the access point, or they're really the website you want to talk to. And there are two main series of algorithms. One is RSA-based, the other one is elliptic curve-based. RSA is ModP, so it's modulus exponentiation. And the other one is elliptic curve. It's a little more complex. I would recommend, sorry for preaching for my own shop in this case, go check my presentation, my Cisco Live presentation. It shows the math in details. But essentially, in elliptic curve, we deal with multiplications, whereas with RSA, we deal with exponentiations. And the fact that we're dealing with multiplication in elliptic curve, you keep the computation simpler. The computation is a whole lot faster for the same level of security as you would have with RSA. So essentially, if you want to say at the same security level, RSA would recommend that you use 2048 or 4096 bits modulus keys and really massive numbers. And elliptic curve allows you to use 256 moduli, so modulus length. Unfortunately, for both, they are susceptible to a quantum computer attack. You've heard about qubits, which are the bits in a quantum computer. And elliptic curve had been made the standard because faster, better, just mostly faster for the same security. Unfortunately, with a small key size, it is more sensitive to a quantum computer attack. And so if you're worried about performances and all of that, stick with elliptic curves because it's better than RSA. But if you're concerned about possible quantum computers, then you have to go back to RSA and very large keys. And even that will not protect you for a very long time once we have a quantum computer. But it will push the horizon a little further out.
If I understand correctly, so elliptic curve, because it's faster, usually you would use that for encrypting communication like ephemeral data, like just thing passing through, right? But the risk of quantum are mostly for data at rest, like secrets that you want to keep forever and things like that. Right? So why would you use elliptic curve for those ones?
Usually you want to use a symmetric key algorithm for encrypting data, so AES. That's what you use everywhere. You encrypt everything with AES. But then at some point, you may want to allow multiple users to access the data. Let's say you need to decrypt the data, Nico needs to decrypt the data. We don't want you to use the same key, so what will we do? We will encrypt the key and store it on the disk, and the key will the key will be on the disk itself, but it will be encrypted within your RSA public key, and you will need your RSA public key to decrypt the key. And that's how we usually store data in digital envelopes. So it's not always like that, but it's one of the reasons like this. Also, certificates, notarized documents, they are signed and the signature is RSA based. The problem with encryption is different from the data from the signature system. So for data at rest, encrypted, we use AES. It's mostly not a problem. The problem with data at rest or the long-term security of stored data is certificates and stuff that is signed. This is dangerous. You have to refresh, but you can wait until we have a quantum computer. You don't worry so much. The real problem with quantum computers is the store now and decrypt later. So attackers, government level, very powerful people, very powerful attackers. They have the ability to tap internet traffic, store the whole internet traffic of worth a few weeks or worth at least a few days, all right? Possibly a few weeks now. It's massive. And they will sift and eliminate what they don't need and just keep what they want to keep. So the bottom line is that they will keep your encrypted connections now, including the negotiation of the ephemeral key, including the Diffie-Hellman exchange. And the key here is that the AES encryption key is protected, is actually generated by Diffie-Hellman elliptic curve or ModP. we can't break it now. But in a few years, if we have a quantum computer, then we can break this algorithm, this Diffie-Hellman key exchange. And now we have the ephemeral key, and then we can decrypt the whole data, the whole set of data that we have kept, or that they will have kept. So even though AES is not directly attacked by quantum computer, though there is an algorithm to weaken AES, which is why we recommend going to 256. The problem is that we have to negotiate the ephemeral key, and that is susceptible to the attack, to the quantum computer attack. And then your data is compromised. There's no free meal. It's bad. If it happens, it's bad. But it's a big if. It's still a long way out. Some people think that it's too much hype. It may never work. I wouldn't bet. I have no idea.
But it's also not worth waiting for the risk to happen. It's a bit like the timestamp problem in 2038. It
Yep.
seems far away, but I'm sure that even we know it today, the solutions are easy. I'm sure that we will still have a problem on that day, and it's probably not.
I would rather compare it to climate change. All right,
or that.
Some people still believe it's hypothetical, right? Whereas 2038 will happen unless climate change kills us first, but that's a different story. But so 2038 will happen, and so not moving is like a bad idea. Period. It's just like trademark bad idea. But quantum, you can always hope that it will not happen or will not happen in your lifetime. It's always a risk, but you can protect yourself against it. Yeah.
So for now, the message is like, don't panic, quantum is not there yet. However, if you really have like company secret that, you are still concerned that in 10 years from now, some government size actors could decrypt, move to something else, right?
Yes, absolutely, 100%. So if your secrets are not worth protecting for another 30 years, it's not a big worry. If your secrets are worth protecting for more than 30 years, it is a really big worry. So military equipment, aviation especially, right? Aviation is probably one of the biggest things I can think of. Banking secrets if you are a very rich person. But honestly, these quantum computers, they will be like satellites. There will be very few of them. They will be very expensive to operate. Very few actors will have them in the beginning, though you can expect banks probably to acquire them as soon as they can because they have optimization characteristics. But so each run of the quantum computer will be worth a lot of money. It will be like retraining an LLM today, right? So you don't retrain your LLM on your laptop while you have a coffee break. You have to say, I'm going to recompile, right? I'm going to retrain my LLM. And when you click submit, then a few $1 million will be burnt. And so you don't want to screw it up. You want to use it for a good purpose. You don't point a satellite with a really nice optic system to a bathroom window because there would be a stupid use of the technology, right? You can't do that. So it will be very targeted attacks anyway, but still no mass surveillance with quantum. At least not with the current technology description today. It will be targeted attacks. So is it important? Is it not important? I think it's time to walk toward the exit. Calmly, the alarm is ringing. There is no smoke. There is no fire yet, but the alarm is ringing. Let's walk slowly to the exit, with discipline. And in 5 years, 6 years from now, the transition will have taken place. And if a quantum computer appears, or like we have a horizon for the quantum computer, everybody will have been happy to get out. And if no quantum computer appears, then we can have a smoke and go back in.
Is now the right time to try to introduce the post-quantum crypto? How does that work?
I guess it is, right? We have to discuss it because there are two solutions to the quantum computer. Either you use quantum networking, and Tim, my colleague Tim, will talk about that way better than I can. We're talking here about using quantum computers, and we're talking also about using quantum networking, which is like optical links where the data has properties. So the way we put the data physically on the wire has quantum properties. It cannot be interfered with. It cannot be watched. It cannot be tapped, if you wish, without interfering with the system. So the attacker would be would destroy the information. So there is nothing to read, and would be immediately detected as well. The drawback is that you need a medium that can support this type of thing. And this has to be today an optical medium. Maybe an electron beam could work as well, but you have to have a line of sight between the two systems. So laser, stuff like that. With atmosphere makes it complicated. We can do it over fiber as well. requires special switching equipment, etc., etc. So it's a complicated technology, and it will not work to everybody's desk or phone because wireless, because copper, because wireless and copper are the key things, right? You're not going to have like an optical tether of your phone. It would be a big mess at the supermarket. So you need classical solution to the problem, and we happen to have a series of algorithms called post-quantum crypto algorithm, PQC for short. So if you see PQC, it means post-quantum crypto, and they are classical algorithms that run on everybody's computer. And the algorithm that is used here is immune to quantum computers. So quantum computers are not magical. They're not fast computers. You wouldn't run Excel on a quantum computer. It's unable to do just a basic addition is complicated on a quantum computer, right? It's just hard. You don't do that. Quantum computers are really good at breaking a specific type of math, like the MOTP and elliptic curve. But it is not good with linear algebra. And now we have these post-quantum crypto algorithm that has just been published actually a year ago now, right? 2 years ago. They have been standardized, and we're busy implementing these standards now. So they're called crystal Kyber, crystal dilithium. They have a whole bunch of names. I can explain where the name comes from the Star Wars lore. But anyway, this is lattice-based cryptography. So you will hear about lattice-based cryptography. Essentially, it's linear algebra. So if you're familiar with matrix multiplication, vector, stuff like that, this is the kind of stuff we do. And you will hear a bunch of buzzwords like lattice-based cryptography, learning with error, shortest vector, and nearest point, all right, and PW. So essentially, there are a bunch of mathematical puzzles, mathematical problems, exactly like elliptic curve and RSA or MOTP mathematics. They present little challenge to the legitimate users and a huge challenge to the attacker. So it's easy to encrypt, easy to decrypt, very hard to attack if you don't know the key. And these run on typically any computer. They have some drawbacks.
I do have one question. So I know nothing about quantum computing, right? How can such computer be great at cracking super complex algorithm and large numbers and bad at additions?
Yes. So if you look at a classical computer, like a chip, it's a bunch of transistors, and the only thing they do is logic operations. All right. So essentially, the core of a classical computer, is a transistor. It has a gate, an emitter, and a receiver. So essentially, it allows the passing of current or not, based on a voltage that you apply on one of the legs. And with this simple transistor, you can easily create an OR gate or an AND gate, and also a NOT gate, and then from here, a NOR gate, and a bunch of gates. So with typically 3 transistors, you can do that. You can create latching circuits. So essentially, the core of these CPUs are transistors, and then from there, we have logic operations. And from the logic operation, from AND and OR, very strangely, we can do math. And so we have like a whole bunch of transistors that are lined up in a very consistent manner. You feed in a binary number by putting the voltage on and off on a few pins, and you get the output of the addition or multiplication on the output of these pins. A quantum computer doesn't do that at all. It takes a particle in a quantum particle, so essentially that has a spin property. And what you can do with this is actually change the characteristic of the particle. You can change its phase, you can change its spin orientation, and a bunch of other parameters. And so you have like, I think 4 or 5 gates, like the H gate, the Adamar gate, and stuff like that. And the operations they perform is simply like modifying the characteristics of the quantum particle. And this doesn't lend itself at all to doing basic math. That's simple as that. It does math in the end, but it doesn't do basic math very well, like AND and OR. It's like as simple as that. It's just the basic construction, the basic building blocks of the quantum computer. And the algorithm that actually breaks RSA doesn't try a brute force. So people like to say that the quantum computer does like all the operations at once, like a super massively multi-threaded system or massively parallel system. But it's not at all the way it works. I think it's a bad analogy, but it's a less bad analogy than the massive parallelization. You can think, so what actually the quantum computer does well, the Shor algorithm in particular is really good at doing a fast Fourier transform. That's actually the operation it does. You can do a fast Fourier transform in real time with a prism. You take light, multicolor, and you break it down, and you have all the frequencies of light in front of you. So if you shine a blue light, you get a blue light out. If you shine a red light on the prism, you get a red light out. But if you shine a purple light, you get two beams out, one purple, one red. All right, so you have done a separation. You've literally done a Fourier transform. Even though this is not at all the way the quantum computer works, it does this Fourier transform really fast. It splits out the frequencies in a system really fast. And with this operation, then we can actually give a boost to a classical computer to finish the algorithm. So it's partial classic computer, partial quantum computer, and you can actually break down the modulus of RSA and elliptic curve. You can actually factorize the numbers. That's actually what it does very well. It also is good at computing the modulus, the logarithm in a mod-p group. But yeah, the factorization is actually the bad thing for us, for Diffie-Hellman in particular.
And so the whole point is that quantum computers don't have a way to break the vector math that lattice
exactly
is doing.
There is no known algorithm, and we think there is no algorithm that actually allows lattice-based cryptography to be broken by this. And lattice-based cryptography operates on a completely different premise than the rest. I don't know if you know what a lattice is. It's just like a set of points in space that are equally distributed, like homogeneously distributed along a formula, if you wish. You imagine like having a cube. If you make it in 2D, in 2 dimensions, you just imagine a grid system, and each point on the grid, each intersection of the lines on the grid is a point, and each point is a point of the lattice. The set of points makes the lattice. And but if I skew that grid, right? So instead of having like a square grid with like 1-on-1 squares or 2-on-2 squares, you actually skew the grid. You elongate it in one dimension, compress it in the other dimension, and then you skew it a little bit so that it's a parallelogram instead of a square. And then you get another lattice, all right? And a good lattice is a lattice where the sides of the square are perpendicular, and it's made of little squares. That's a perfect lattice. A really bad lattice is when you have a very compressed lattice, like a very acute angle on one of the lattice, and one of the sides is really short and the other one is very long. And if I give you a point, random in space, and I say, what is the nearest point belonging to the lattice that is close to that point? It's a hard problem for a computer. It's easy for us in 2 dimensions because we can see it on a sheet of paper. If I put it into 3 dimensions, you're going to twist the stuff like for a long time before figuring out. And but the problem here in the math we use is in 256 dimensions. And a computer, yeah, you do it with massively huge lattices, huge numbers. And really crazy angles in the skew of the lattice. And this is a hard problem to solve even for a computer. We just don't have good math for doing that. Classical math shows that there is a limit to the precision we can get. The attacker will normally not break it unless we have a major advance in cryptography, in mathematics. And we don't have a quantum algorithm for breaking that either.
And graphic cards, I mean, they're better than a CPU, but they're still not changing the game at breaking.
With the size of numbers we're talking about brute force attack. This is why lattice-based cryptography took such a long time. So we had the concept a long time ago. We had to figure out the exact math so that it wasn't breakable by classical math or easily, like the no shortcut, and by classical computer. And then we had to tune the size of the numbers and the number of dimensions so that it is strong enough to a brute force attack. And the drawback is by protecting yourself against the brute force attack means that we have to deal with a large number of dimensions and really massive numbers. And the matrices that we have to transfer are really, really large. This means that there is a lot of data to send between 2 computers before they can actually compute the shared ephemeral secret. So you are going to see that the lattice-based cryptography algorithm, they take a lot longer to negotiate. So even though we have them and they are in development, we are going to now have to measure the impact on system scalability, tunnel per second creation rate, total scalability of the system, cost on the CPU, all of that.
But it's only for the negotiation part, right? Once it's negotiated, then it's as easy as before, right?
That's right. But so on small scale system on your phone, it's not too dramatic. But on the concentrator that aggregates millions of connections, that's going to be a problem.
And I've read something about the fact it introduces an error in the lattice system. Like you give a slightly different vector, and then when you have the key, it's easy to find back what it was. But without the key, it makes it even less possible.
Exactly. Well, that's the error stuff. So that's the exercise, the mental exercise. I said, if I give you a point, like what is the closest point? That's exactly the problem we have to solve. So how does encryption roughly work? It's better explained again with the visual on the presentation, but essentially you take a lattice as the sender, right? You take the lattice of the responder, and it's a badly skewed lattice. It's like really crazy, stupid lattice. You choose a coordinate point, which is the message you want to encode. So you split your message, which is a number, and you break it down, and each part of the breakdown is a coordinate that takes you somewhere in the lattice, and you choose a point. I mean, you end up selecting a point on the lattice, and then you, instead of sending this point to the receiver, because now everybody would know what the point is, you introduce a little error. So you shift the point a little bit. You create like a little error around that data, and you send the point with the error, so the misaligned point, to the receiver. And the receiver has a way to figure out what is the nearest point. And once it knows the nearest point, it means it knows the point on the lattice that you meant, so the without the error. And once it has the point without the error, it's able to recompose the message that you had.
Pretty nice. And then I have a weird question from a history standpoint. All the other crypto stuff is I mean, math theory that existed already, right? Somehow. What about this vector based? Like, did people invent this just for the post-quantum crypto, or was it just theory that existed and someone said, hey, we could use it to our benefit? Or where does
Well,
it go?
actually, just like the rest of crypto, I mean, linear algebra was there for a long time. The problems existed for a very long time. They were not very practical system, less practical than RSA and the rest. So if you look at elliptic curve, right, it was invented like about 2 centuries ago, right? The mathematics around elliptic curve started about 2 centuries ago. And of course, it evolved over time, but nobody knew really what to do. It was a curiosity. It was interesting, but a curiosity. And then suddenly somebody figures out that you can do crypto with it. And now there is suddenly there is like a spike of interest, and a lot of mathematicians start, crunching the theorems and trying to break it. I mean, some try to improve it, some try to break it, some, and so there is an acceleration. Same thing in lattice cryptography. This linear algebra is around us all the time. If you go to university or high school in general, you will do linear algebra. You cannot avoid it. I mean, in technical curriculums at least. But of course, there has been a huge acceleration with the interest of post-quantum crypto.
And do you think that there are other mathematics systems that we didn't think were useful until now that could be used for new cryptography, new systems, or to actually break those type of cryptography for quantum computers?
To answer this question, I need a double shot whiskey and a cigar.
We can arrange that another time.
Because, I mean, look, we can simplify, bring the explanation. I live with a simplified explanation of cryptography myself. Everybody lives with a simplified explanation, but this is futurism. And so, yes, I do believe, right? But I do believe, like, I could be wrong. I believe that one day we'll have quantum computers, but to be honest, I'm not so certain. So, yes, I think there are some, but I don't know which.
To me, it shows the magic of the human being, where probably people did theses for decades about stuff and problems and theorems, and people attending the thesis were like, what's the point of this? It's completely random. And then decades later, hey, how about quantum, cryptography with this?
Yes.
Oh, this is useful. Oh, nice.
Actually, it seems that in the mathematics community, people got a little bored of elliptic curve and everything. It was like boring. And they actually took the break pretty happily to lattice-based cryptography because it kind of renewed the field a little bit. It dusted off a bunch of things. Yeah, I guess change can be positive. It's not great when you own a system, when you manage a network. Your core business is, essentially selling goods and services to people, and the network is just a mean to an end. And the fact that you have to invest and upgrade your cryptography, I mean, let's face it, we could all deal without that. It's a bother. But yeah, it's like the rest. You have to put petrol in the car. all right, or electricity. So that's that. You have to take it for maintenance, and from time to time you need to change the car, even though you loved it.
Okay. I have one last maybe weird question. I love weird questions. It feels to the average random network engineer that every 6 months, every 1 year, there's a notice like, oh, move to this version. It deprecates these ciphers that are not secure anymore. And now we only offer these, blah, 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 and upgrade your key length. And it feels like we have decent CPU computing power. How about we just bump everything in one go and then be safe for a good amount of years? Like, why is it constant that we have to? I mean, I've still see some algorithm using MD5 and now, they're deprecated. Why do we stick with old crap like this?
So there's a few things. So first, there is a huge reluctance in moving to new systems. You have to uplift your entire system. If you still have, let's dial back, let's say 10 years ago, right? People still, actually even today, some people are still running Windows 95. They shouldn't, but they do. and you can't afford breaking everything and replacing everything. And it's just like we have protocols and leftovers in some protocols because of someday PDP 11 or a VAX or a mainframe. They were doing things a certain way and there was no replacement, and we had to deal with it. I mean, why don't we still have proper TCP path MTU discovery? Why are people still blocking ICMP? Why? And it's always the same, because you have legacy systems you can't afford to uplift, because you have code that has never been uplifted, because licensings were not upgraded, because the software is not anymore under development, or because you have to put your resources into a feature rather than an uplift in your system. So it's just practicalities, simply for practical reason. Should people bump it? Yes. Should people have stick to IKE and IPsec for their VPN instead of using TLS and DTLS and all these things? Yes, of course they should have done that. I never understood why people went for TLS. It was an inferior protocol until TLS 1.3. And let's face it, even TLS 1.3 is, not as good as IKE. It will get there asymptotically, but why did people stick to TLS for VPN, right? There was no good reason. It was like a marketing debate, marketing dispute, but it was bad. And so we had bad VPNs with like holes, big like a mammoth, simply because TLS was so broken, or SSL, right, as it was called, was so broken. But still, we did it because marketing had its way. Mathematicians are not immune to that, right? Oh yeah, but my algorithm is better. Oh, this algorithm is better. And so we have a plethora of algorithms to choose from. No, I think that people are getting a little serious. They look at NIST and say, okay, NIST, what should I use? Okay, this is a recommendation. This is what we use. And so you have much less. My recommendation to everybody would be this. If we had to put one for the day of today, make sure that you don't have anything less than TLS 1.3. If by chance or lack of chance you still have TLS 1.2, it's not so bad. Make sure that you use Diffie-Hellman, so ECDH or DH at minimum. If you're not using ECDH or DH in Diffie-Hellman 1.2, or you have a lower version of TLS, don't worry about the quantum computer. Your data is toast anyway, so you lost it already. Don't worry. There's no point in worrying about the future. So TLS 1.3 or TLS 1.2 with Diffie-Hellman. Ideally, you use RSA and classical Diffie-Hellman instead of elliptic curve today, if you again worry about the quantum computer, and you use key size of 4096 bits for RSA. That's really where you want to be. But that's the simple recommendation. And then you wait for the vendors, Cisco among others, to come out with new implementations, like the implementation of the post-quantum algorithm. And then you look at the data sheets, you check if your systems are going to survive with these new computations, with this new math. And based on that, you plan your move, and it will probably take you 4 or 5 years from now. I mean, not everybody. Some people will be able to switch next month. Some other people will have to wait that all their systems are ready before they can do the move. Some other will have to wait for the end of maintenance because they don't want to swap the hardware when there is no reason. They will just wait for the next renewal cycle. So I would say it will take another 5 years for everybody to upgrade.
So it seems the key message is also to have like a good inventory of what do you have in your company.
Yes.
What are the weakest points? What is your upgrade plan to move out of there or mitigate it one way or another? And
yes,
that already takes you very far, right? Knowing what you have and not being passive.
You actually mentioned something critical. Upgrade your systems, keep them to latest and greatest, not bleeding edge, all right? Like GD, you look for GD software. I mean, ideally, if you can, sometimes you have no choice. But outdated softwares are, I mean, they're sinking ships. Essentially, don't worry about crypto if you have not upgraded for like 5 years or 10 years, because the attacker is already in through another way. And they have already taken your data differently. And if you have not been hacked, it's because you don't know you have been hacked. Simple as that.
Sad but true.
If you don't know you've been hacked, is it that bad? I mean, you just
Well, you
Have
live
you really
better. You sleep well.
you live happily, yes.
Yes.
Okay.
I do have one more question, and sorry, that probably will be another cigar and whiskey question. How is AI impacting the research on quantum computing and quantum cryptography, if there is any?
I do not know because I am not a researcher in the field, right? They have code because even to program a quantum computer, you need classical code. I guess they do the research and they use AI. I have no idea, to be honest. AI does not affect cryptography in general, right? An AI will not break AES, or you cannot give it a piece of text and say, "Find me the key." All right, here is a piece of text encrypted. Here is the plain text. Find the key, or something like that. It doesn't work. There is too much entropy. It just won't work.
That's fair. That's cool. Thank you.
Okay. Well, Fred, thanks a lot. That was reassuring somehow.
Thank you.
That there's a clear destination and a clear path. So okay.
Yeah,
it's not too bad.
there's a, like I said, there is a path. Plan it. Don't linger. Move for it. But like I said, check your data sheet, right? So like you said, can't we bump? Yes, a system today, for classical algorithm, we can bump the algorithms, but with lattice-based cryptography, the impact is going to be bad, especially on concentrators. The end nodes, not so much, but the concentrators will suffer. The negotiation time will increase, TPS rate will suffer.
And last but not least, go to ciscolive.com and type Frederic Detienne and look for a very surprisingly understandable crypto presentation.
Yeah, it was great, actually. I loved it. So very simple on the math, actually. So
Thank you.
that's cool. Thank you.
Thanks for listening to this episode of the Cisco Tech Stories podcast. You can subscribe to us on the Cisco Podcast Network in SoundCloud or your favorite podcasting app. You can also find us on our own channel called Cisco Tech Stories in every podcasting application. Thanks, and see you next month.
Static whispers hum the wires, fingers dancing, sparks on the keys. Echoes of codes long expired, in shadows deep where no one sees. A ghost of fish haunts the machine, silent gears turn in the unseen. Loop it again, till the meaning fades, till the message bends. Carved on stones, ancient and raw, symbols cracked by the hammer of thought. Scrolls burn, but the secrets claw through the ashes of wars they fought. Enigma whirls its ghostly song, cogs and wheels spinning wrong. The cipher's curse twists and turns, every secret yearns and burns. Unlock the truth behind the wall, but every ashes of wars they fall. The cipher's curse, no and no star, code of the world, code of the heart. Ribbons of light through silicon veins, data flows in encrypted chains.